So what I want to do today is finish this whole business of how Newton's laws of motion can be used to explain or to describe demand in economics. Our whole effort consisted of comparing two publications. One done by a guy called Isaac Newton. He is basically the founder of mechanics as we know it today. Before Newton, there was darkness. There wasn't darkness, but there was Aristotle, who believed that you needed a force to keep our body moving. You know, it was the wrong notion of force, okay? With Newton, we knew how it was. It just took us a few hundred years to figure out that it was all there. And then on the economic side, there's another publication by a guy called Alfred Marshall in the end of the 19th century here. He wrote a book called The Principle of Economics. It's a very good read. And that, for the first time, laid down the idea of demand and the demand and the supply graph and these kind of notions. It's not that they didn't exist before, but it was not that a notion of force didn't exist before and a discussion about what it really was. It's just that Marshall was the first to put it down, and this is where the terminology comes from. So he established these concepts of price elasticity, price, demand, and all these things. He just wrote it down, and from then on, we just talked like him, all right, with some modifications. So that's what we're about to do. You can get the book. It's just on the internet. I think it's for free now because there's no more copyright. And I've spent a lot of time reading it. It's been fun. And this one, there's a really great translation, a new one, by some people at Berkeley. Boudens is one of them. So it's also really readable, you know. And both books are pretty readable. And one of the things I want to do here is match them up. So go back to the basics and how these old timers did it. And then, of course, there's some new insights. I'll put those in, but there are also some bad interpretations, and we're going to leave those out. All right? So let's get going. And I'm just going to recap some of the stuff that went before. It's really good because you just got to visit this stuff often before you really get it. So Newton, he starts off with something that he calls a definition section. And in it, he first defines what he calls quantity of matter. So matter is to him the stuff that matters for mechanics. So when there's no matter, he's got nothing to say. It doesn't matter to him, all right? Now, similarly, for Alfred, that what matters is the existence of demand, all right? So if there's demand, then we're talking, and if there's no demand, there's no talking. So you see intuitively, if you want to pair them up, this idea of matter is going to correspond to demand. Now, nowadays, we still talk a little bit like that, but we instead, rather than saying quantity of matter, we have two terms to describe the situation. First is the phenomenon of matter. This is what we now call inertia. So this is the phenomenon. And then there's the measurement of the phenomenon, all right? The quantification, I should say, all right? Not the measurement. And this is the quantification. And it's a mass, and it's a number that's bigger than 1. So it's a real number, and it's bigger, and not than 1, it's bigger than 0. And when it's equal to 0, then there's no demand. Okay? It's not negative, right? Never. Now, in this modern lingo, so the quantity of matter becomes the mass, and matter itself is inertia, the presence of inertia. Right? Now, intuitively, this corresponds to the idea of the demand in economics. So you have this space, stuff is happening, but what you're looking for is when you have actually demand somewhere. All right, so this is the idea. Inertia, what you have is somehow when you have inertia, you have something that at least will keep a constant velocity. You can measure motion if you have inertia. If you don't have inertia, there's no idea of motion. And the nice thing about an inertia is it preserves this motion, all right? Unless you stop messing with it, with applying a force. Okay? What's the nice thing about the demand? It also preserves motion. It preserves the flow of goods. So if there's demand for apples or oil, then there's a flow. And if the demand is constant, this flow would remain a constant. So if you're running around your space and you encounter some demand, you say, hey, God, I got it. This is starting to matter. Okay? Now, we can quantify the demand in a similar way that you're going to quantify inertia using the mass. And this quantification is by a number that is bigger than 0, the way we are going to define it. For economists, it's smaller than 0. And it's called the price elasticity of demand. And why is it always in one direction? Because what the price elasticity does, and I got a quote from, you see I'm getting better with this beamer. Huh? So I got a call-out quote with a very obnoxious yellow with the background. Huh? So we will see that the reason the price elasticity is always a positive constant is because of what they would call the law of diminishing marginal utility. All right? So it is a fact that the more you get of something, the more you're receiving of something, the less you like it. All right? One apple, you're willing to pay a lot. Second apple that you get a day, a little bit less, and this. If that is not the case, we will never have economic equilibrium. Okay? People are willing to pay more for everything, so everything will just blow up. This is what causes stability in general. The same way that a mass is not negative, that it starts like accelerating like a crazy guy if you pull at it, right? Yes. Could you specify price elasticity a bit more? Because we will. All right? But okay. Instead of saying we will, let's just do it. I'm just going to remind you of what you see, right? Huh? Here is a price. Here is your quantity demanded. This is your typical supply line, right? Huh? Oh, this is demand line. Call this the supply line. Let's use the supply line instead. It's a little easier, right? Then this slope is going to be the mass, right? Okay, let me stop you. This part was clear. I have to elaborate a little bit more. In my literature survey, I encountered elasticity quite a lot, but they tend to use it for everything. When they have regression for one dependent and for independent variables, every coefficients, they call them elasticity. Yeah, but not a price elasticity of demand, all right? Yeah, okay, but if the dependent variable is price, then it's always price elasticity. But this is the coefficients between price and demand. Yes. It's called, or officially it's called the price elasticity of demand. You have also the interest elasticity of credit or something. That's different, okay? They call everything an elasticity. We only call the constant of a spring an elasticity constant or a stiffness. We deal with it, all right? Huh? They don't have the distinction between inertia and elasticity and the damping ratio. Everything is an elasticity. They just say the elasticity of this with respect to that, all right? Okay? So what we will, yeah? We will use price elasticity of demand, and all the other elasticities will get a different name, different definition, different. Right. I mean, they will. It's better said that to inertia or mass corresponds the price elasticity of demand. You can also look at the convenience elasticity of your stock, right? Or the storage elasticity of your convenience yield or something, and that will be the stiffness, okay? Okay, so that's the better, or you can look at the credit elasticity of interest, you know? And this will be, what will this be? This will be the moment of inertia. No, this is the moment of inertia, huh? So it's the moment of inertia then. So you gotta see that they don't have this terminology of moment of inertia, you know, stiffness, They just call everything elasticity, and in a sense it is, you know. So elasticity is really, well, you know, there should have been a -1 here. It's the inverse, right? So what does inertia mean? It means that if you want to make this thing change velocity, it's just hard to do so, right? So it's a little bit sluggish, it's stiff, right? So the inverse of the elasticity is the ease at which you can do this, okay? Huh? All right, so, you know, if you don't know that Newton is the one who came up with the word inertia, he just plopped it down. And if you read him, you can see him struggling, finding a good word, and then he just called it inertia, right?
Yeah, okay. I think you answered the question.
Good.
Question quite well. Thank you.
Uh-oh, I'm going the wrong way. The second definition he makes is what he calls the quantity of motion. And we now call this the momentum. In Dutch, it's the impulse. Huh? So there's a word in English called impulsion, but it's not used in a technical context, just when you have a horse or something. So these also corresponds to something to concepts in economics. So when you have a quantity of motion, did I have a no? So how much? If you have demand somewhere, how much is what's the price? Well, the price is exactly, you know, what you are willing to buy. How much are you willing to buy? That's this idea of quantity of motion. And this willingness to buy, that's going to be formalized and quantified in a price, okay? So this is, again, the phenomenon. And this here is the quantification of it. Huh? Economists will use this. So if you read a Marshall, sometimes they call it willingness to pay or willingness to sell, a little dependent. They don't use vectors. And for us, momentum, of course, is a vector quantity. So we would call the willingness to sell the negative of a willingness to buy. All right, but they don't do that. So they just keep switching terminologies to use only positive numbers. All right? So again, you see the same pattern here. Newton doesn't have a word for it. He doesn't really have a word for inertia either. That came later. And, or he came up with it, but later in his book. Here he calls it quantity of matter. Huh? And the quantification is done in this thing called momentum. All right? Now, we will call this the price. But what's important to see is that it's the what is nowadays called the reservation price. Marshall uses this term called purchase price, and he explains that's the price at which you or the consumer or the agent wants to purchase it. Okay. So there's going to be lots of different prices. So don't get confused and think there's some objective price. That's not the case. There may be some equilibrium, in which case you may think there is an objective price, but there is no objective price for the same reason that there is no objective momentum. Every body, every piece of matter has its own momentum at that particular time, okay? And every economic agent, an economic agent is the embodiment of demand, right? So you just think of demand as the agent itself, okay? Because every location of demand is what we will call an agent, and that has its own price. And these prices interact. This is precisely why you have trade, or why you have transfer of energy in mechanics, because the prices are not the same. You know, these things will crash into each other and exchange momentum or exchange the price, right? So my price will lower and yours will rise as I buy something. If I buy something from you, I will lower my price and you will raise your price, okay? And at a certain point, I don't want to sell anymore because our prices are equal, huh? Okay?
And the reservation price, but the transaction price is objective price, right?
Well, even that is not objective. It's just the moment that the price of two agents that interact happen to be equal, and at that point there's a transaction that you could call the transaction price, but even that is not the case. Because normally there is a bid-ask spread, there is some kind of difference in the two, and it has to be absorbed by the market or something, okay? Huh? So there is no objective price. The only thing, sorry?
There's one price, at least, where I get goods and you get X amount of money.
Yeah, but that's just a point in time when the collision happens between the two bodies, okay? Huh? Okay? We'll get to this. Huh?
And is there a distinction between the price as you are defining it now and the value?
I don't understand the question. The value of what? Or the value of the goods?
Exactly. I valued like this, so I've got the reservation price in my head, the transaction price, the real cash transferred. I thought the value was more a personal thing, which...
No. I see what you're trying to go to, but don't think of that. Reservation of price comes from auction theory. And I have my own price, and I reserve it for that price. That's the term they use, okay? It's when you're at an auction. If you're at an auction, you have your reservation price. So beyond that, you will not buy it, right? It's the maximum price that you set, okay? And for the seller, it's the lowest price. Beyond that, he won't part with it, okay? That's called the reservation price. Okay.
And how does this compare to value? Does this also...
I will get to that. I will get to that when I do the third law. Okay? Because value is a state variable, and we're just saying this is just a definition. You know, we haven't done any modeling yet. I'm just telling you what the definitions are that Newton makes, and then he says his laws, and then he tells you what all these things really mean and how they relate. Okay? Huh? All right?
If you come to it, it's fine. But
yeah.
I try to place them next to all the other definitions.
No. That's fine. That's fine. I'm just. I just want you to realize that this is all we're doing right now, right? Huh? Okay. Yeah. No, it's okay. It's okay. So the third thing he does, it's actually the fourth, the fifth, and sixth. He goes to all kinds of forces. Newton. This force, inherent force, a lot of this terminology doesn't exist anymore and has been replaced by other things. But the first thing he talks about is this idea of a motive force. And that's the force that motivates the mass to move, okay? And change its momentum in his head. He hasn't defined yet how it goes. He just lists these things and describes them. This Marshall would call a want, right? So and he also uses the word desire. Huh? Usually that's a stronger one, so that'll be a stronger force. And you can also think of needs. It's an extremely strong force, maybe like a constraint force or something, okay? But the general idea is a want, and a want is the thing that drives the price upward or downward. So it's your motivation. So the want, you can think of that as the economic motive force. In electrodynamics, the equivalent of this motive force is an EMF, right? The way Maxwell defined it, electromotive force. So it motivates those electrons to go forward. So what is nice about this idea is that this idea, it's called an anthropomorphism, which later writers, especially after Ernst Mach, who went through physics, they said you shouldn't do that. Anthropomorphism is that you explain nature as if it were a human being, all right? So you say that this thing is motivated, and you think of this mass as being sort of a human being, an animate thing Anthropo is anthropology is people, right? And then morphic is shape, right? So you give it a shape of a human. And that became very, very unfashionable after a guy called Ernst Mach, who tried to make physics more objective, more about, inanimate matter rather than evoking our own free will, all right? But these guys were not so bothered by this, and we still call this the motive force, or electromotive force all right? So in economics, what I like about it is, of course, in economics, we have no problems with anthropomorphism. I mean, we're talking about human beings, okay? So for me, what's kind of fun about reading Newton is that it's almost like he has, in this idea of force, he has the economic engineering analog in his mind to describe what nature is doing, okay? And it is just for us to kind of discover this obvious thing, right? That, I mean, think of Kepler. He thought of angels flapping their wings and trying to push these planets on, right? They were motivated to present God's work and how the celestial sphere should go in this perfect circular fashion. All right? Then Newton has some other names. I'll forget them. It's all translated from the Latin. It's inherent force, and I can't remember, impinged or something. But there's what we now would call the applied force. It comes from the outside. Okay, and economists make a big deal about a distinction between exogenous and endogenous. Exogenous comes from the outside, external, and endogenous in the inside. Okay, so the want is endogenous to the agent, and it's really interesting because Aristotle's idea was that everybody held on to until Newton and even after, was that a force was required to continue the motion, all right? So they had this feeling that everything came to a standstill and rest was only standing still. But so in order to keep it moving, you have to keep applying a force, like you have to do in a car. You have to keep pressing the pedal, otherwise the car will come to a standstill. They didn't have the idea of friction as being a separate thing. And it's really interesting that some famous guy, if you remember, maybe it was Aristotle himself, proved the absurdity of the existence of, he proved that vacuum couldn't exist because he argued that if it exists, things would keep moving at a constant rate, and this is so absurd that cannot happen, and therefore vacuum doesn't exist. So you can see how the reasoning, they got stuck completely on this idea that some external exogenous thing was needed all the time to get you moving. There was no concept that the force was stored in the mass, right? And this is now what we call momentum, right? So momentum is stored in this mass. But there were people who were saying, well, how is it possible that if I throw a ball or launch a projectile, that somehow that force that I applied stays in that thing at least for some time before it damps out? So they were confused about it, okay? And Newton, of course, cleared it all out. He says there are two types of forces. One is the endogenous thing, is you apply this force, and then it just goes in there, and then it just keeps going. It's endogenous now to the thing. It's so is it with wants, okay? So The want is endogenous to the agent. He wants this, and he acquired them from somewhere, and now he's just following his whatever he accumulated. All right, but then of course he can be jerked around by other forces coming here, somebody raising the price or doing this, and then now then there's some exogenous forces acting on him. All right. So there's also something we would call a reaction force. This is something we'll talk about when we talk about the third law. And Marshall and many afterwards talk about that a want, you can only have a want if you at the same time exert the effort, okay, to balance out this want, okay? So a want cannot come from anywhere. You cannot exercise this want. What you need to do is start working. So that's an effort where you expend something, and this will balance then your wants, okay? And then you're in business. And we'll see later that this is action and reaction pairs when we deal with the third law, okay? So you have wants and efforts. Then Newton also talks about centrifugal forces, and I can't remember whether the Coriolis Force is there, but these are all these other fictitious forces. And economists will call those effects. So they'll have the substitution effect that you will tend to replace one thing by another item. If apples are too expensive, you'll start buying more pears. And you can think of these effects, and we'll talk a little bit later, like these fictitious forces, like a Coriolis force. So suppose you're reorienting yourself, and you're sitting on a big merry-go-round in a playground, and you throw this ball out. Then this ball won't go straight out; it will make this curve. Of course, for the observer from the inertial reference frame, the ball will look as going in a straight line, but you're moving away from it. So it almost looks like you're substituting a little bit of this stuff for that stuff. But it has to do with your own state of motion. So these are effects on demand, and there's the income effect that is a sort of a centrifugal force. Some of these you can describe by what we would call fictitious forces, or not real forces when you're not in an inertial reference frame, basically. Okay?
But aren't those forces kind of reaction forces?
No, you see, a fictitious force. Sorry?
What they call centrifugal force, for example, that's some kind of fictitious force, right?
Yes.
And that's the reaction force, I believe.
No, it's just the force you would have to apply in order to keep the thing within where you want it to be, all right? So to counteract the effect. Okay, that's what it is. So it is because you're not in an inertial reference frame. So if you have a Coriolis force and you're just standing still, and the body will go in a rectilinear line, and you will just see it going away from you or going like that. But now if you're turning, this is not going to happen, right? So, but there's no problem. There are no reaction forces. There's no forces acting on that thing anymore. There's no problem. You're just being silly. You're not in an internal reference frame, and the laws of Newton are not valid, right? Huh? Then you can say to yourself, well, I mean, suppose that I am in an inertial reference frame, or what is the force that would want to force it back to, now going straight in from me? Now that's the Coriolis force, right? Or you're sitting in the centrifuge, and I don't recommend doing this at home, and you're looking at your clothing, slamming to the side, huh? And you can say, well, I don't know why all this crap is, or your car, you're turning left. I don't know why I'm slamming against that. But anyway, the door will push me back, right? Or my seatbelt will push me back, right? And that is how we measure the size of this fictitious force, right? Huh? Okay? So it's not a reaction force. A reaction force, we'll get to this. This is the third law, all right? And that's how efforts come into play here, to balance your wants, okay? That's why you can buy bananas all you want, but you got to work, right? You got to do something to be able to do that, all right? Okay. So here's what Marshall says: human wants and desires are countless in number and various in kind, but they are generally limited and capable of being satisfied. Now, I left this in the quote basically because satisfaction is going to turn out to be, the rate of satisfaction is going to be the power, right? So the force, you got this want, you got to fulfill it, you know, so you got to pair it with a flow of commodities, and that product will give you the power, all right? And that's the way these people, Marshall will think about it. He says there's wants and there's efforts, and all of them have the capacity of being satisfied. So we have forces, positive and negative forces. It's a vector quantity. So an engineer will say the following, right? Force is a vector quantity. So don't think of action and reaction here. It's just positive or negative. It's either a want or this, I don't know, huh? Whatever, huh? And when you multiply it by velocity, you get power, right? Huh? Okay. All right. So this is so far for the definitions. So then he has a second book, and it's called the Scholium, and he inserted that later. And this was just to lay the foundations to tell everybody what time was and what he meant by space, because it was a little bit confusing. So we talked time, there's not much to say, except that Newton chose, he just writes down, time is just absolute, it's the same for everybody, and blah, 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 right? And this is what we will do too, you know, just look at your clock, you'll know what time it is, right? Now, famously, of course, this happened not to, this later was proved by Einstein to be wrong, all right? So time depends on how fast you're going, you know, it's all relative, you know, but we're not going to concern ourselves with these kind of details. So this is just fine to us. Then the other thing that Newton does is he introduces first absolute space. That's just standing still. So he's still saying, how does this relate to Aristotelian mechanics, where we think rest is standing still? So somehow we have to know what standing still is. But then he says that is of not so important value. What we have is relative space. So you just know that you're going at some constant speed, you know, and you're only looking at how things look with respect to somebody else's space. And this is what he calls relative space. And that's the kind of space that we'll be dealing with as well. So I'll be talking about the principle of relativity, the Galilean principle of relativity, and how that relates to demand. So this whole idea of relative space, he got that from Galileo, and I have to say, I just can't help but marvel at what Galileo did, because he was sitting there with everybody. Just think about you being him, and you're sitting there, and everybody's convinced that everything, rest of equilibrium is just standing still. Okay, that's kind of the thing to do. Now, how do you prove that that's not the case? How do you prove that things, you know, will maintain a constant velocity? It's not so easy to imagine, right? And this is what the guy did. So he built a ramp, and he put, and why did he make a ramp? Because he put a little bullet, and it would roll down almost friction-free. And he would notice that it would go down like that. So he starts discovering gravity, and he would clock it. He sees that it would accelerate. But then what he did, he built another ramp, and that was, as soon as it came down, it would come up again. All right? He did this in 14-something, right? 500 years ago. Huh? And then he would notice that it approximately would come back to where he let the ball loose on the first lamp, let the ball go, all right? We know that that's just conservation of energy, but he didn't know that. There was no energy, right? But then how does he use that to prove that a body at rest goes at a constant speed? Well, he made the angle that the ramps make with each other smaller and smaller. So then he noticed that they started from further and further, but you could just get them to go from very far to the left to very far to the right, because it will go gradually down and then gradually up. And then he hypothesized by continuity, or if you want to be fancy, the intermediate value theorem, that if you made it flat, it should just go from minus infinity to plus infinity. And therefore, a body at rest goes at a constant speed. So when you read that, you take off your glasses if you have them, and you go, well, wait a minute, that's a nice way to reason. Okay, I'm convinced. It must be friction. We must have been wrong for all these thousands of years. So this piece of reasoning, this is what you want to take to, this is what you want to bring to economics. You say, well, when these people are demanding that, okay, who knows where they came from, what there once was, and how they accumulated those. But you can imagine that, if that's done way in the past and now nothing is happening, then they're just going to keep buying the same stuff all the time, Just like Galileo considered that, all right? And the other thing you'll notice is say that this motion is not going to depend on how much the guy has already bought. Every day is a new day, like it is on the stock market, You don't care what you've done before, only the present matters and what's going to happen in the future. So this space that we're in has to be what they call homogeneous. Any point here is just as good as any other point, it's just as good as any other point, it's just as good as this point, it's just as good as this arbitrary zero I took here. So economists, if they say this is Abby and this is Octavia and all this, that's just a choice. I mean, they could have taken any other players. It would all be the same, all right? So if I just look at the space without the inertia there, it's got to be homogeneous. There are no special, points. It's just when I bring economic agents in that I get special points, okay? And then the space starts curving and it tends to move towards there, just like gravity maybe, okay? But if I take everything away, I get this space which is homogeneous. Okay, so only the flows matter, only the velocity matters in that space. And that's what you see in the demand and supply graph. So they will look like this, only the velocity is here and the price, and this is what it is, and there's no other axis saying the amount, and now it also depends on that. No, only the velocity matters, right? The space is homogeneous, okay? The second requirement for this space, and these words homogeneous and isotropic, they're modern words. And this is what we, well, if you read more modern things like Landau and Lifshitz, this is how they would set it up, these more mathematical approaches. The other requirement that Newton has is that the space is what we call isotropic. So if we look at our own space, all directions are equal, right? So if that's not really true because gravity makes a special direction. But if I leave out this and I just look at the table in front of me as a plane, all directions are equal, okay? So I can just throw a ball like this and I can turn the whole table and do the throw and it's all gonna be same direction. So my laws are also invariant under rotations of this space, okay? It doesn't matter how I orient my apparatus, okay, in the plane. It matters, of course, with gravity, but think away gravity, then it won't matter. All directions are the same. This is what they mean by space being isotropic. By the way, that's why we have angular momentum as a thing, because we know that an angle is something that doesn't matter. So if it doesn't matter, then how fast you go through it won't matter, and you can get a conservation law of angular momentum. So it comes from this idea of isotropic. Now, what's a little bit funny is that we tend to measure the direction using an angle. So we use the cosine and the sine and all of this. And for that, you need a Euclidean metric. You need an inner product, and you need to do a Euclidean metrics. But there are many other ways of measuring angles. You have hyperbolic angles, you have projective angles. So what in an economic space like this, these edge-width boxes, you don't have a notion of angle. This is not 45 degrees. I mean, you just know that these are, there's no way of making 45 degrees because you don't know what the length of this thing is. But nevertheless, you can look at a direction and you can use the slope, right? So there's the ratio of Q1 over Q2. And that's what we call the composition of the basket. So you're buying baskets with a certain composition. So many apples together with so many pears, and then if I have equal apples and pears, I will just have this direction, and this will be 1 basket, 2 baskets, 3, 4, 5. And they're definitely different from these baskets, okay? So we can think of the space as having these directions that are given by compositions, all right? Now these two things Newton has to put into place, because when he formulates his first law, and this is what we're going to do, is that it will have to be rectilinear motion. So you're buying these goods at a particular basket, the composition of the baskets, and you're just buying more of that along. You're not like substituting one for the other, okay? All right? So this is how you have to see the notion of this commodity space. These are commodities as being similar to Newton's space of ambient space. All right? Here I have a picture. You know who made this picture? It's Huygens. And Huygens, remember, he was the guy who fixed the problem with the momentum law of Descartes, who took away that absolute value sign. And you know how he did it? He went to Galileo's principle of relativity, and he realized that the motion was relative. So here he has this guy in period costume is standing on the shore, and the other guy is standing on this boat. And Huygens, he lived right here on the Vliet. What is it? Yeah, the Schie. Huh? So here is the Schie River. If you go, you can see his house. It's, I think it's in Voorburg, huh?
Oh, that's the Vliet.
That's the Vliet, huh?
Yeah,
the Vliet. Huh? Yeah.
Then you pointed the wrong direction.
What?
That way.
Oh, I pointed in the wrong direction. I had the wrong composition. Huh? I thought space was isotropic, but. So he is very close to Delft. He must have been imagining this thing and this barge here. So this guy is doing the relative. This is like the center, the inertial reference frame, and this is the guy moving. So he's looking at relative motion. Isn't that interesting that these guys are actually thinking about it? Huh? So that's why I put it in. Okay. What I'm trying to do is make this development of mechanics that you just get like, I mean, they feed you guys like a Strasbourg goose, like they just open your mouth and they throw the stuff in there and then see whether your liver gets bigger, huh? When they teach you mechanics. So what I'm trying to do here is to see how economic engineering goes in the same kind of development of the subject, where you get a good feel for what all these quantities mean and that it's the same struggle, okay? So please pardon all this historical stuff if you're getting tired of it. All right. So now that we have done that, we're going to talk about his laws of motion. We did already, and what I want to do is I'll go through the ones that we did last time, and then and do all the new stuff after the break. All right. So then he writes down axioms or laws of motion. That's just what he says. So he calls them axioms too. So you see, for him, there's no big difference whether it's a definition or just a law of nature. Huh? And the first thing, law we talked about, and this is also called the law of inertia. And in economics, I would say, and it embodies the idea of rest, and this is what I would see the idea of economic equilibrium, all right? So economists don't really define what equilibrium is. Sometimes you see that's when the prices are equal. Sometimes, normally they find it in a rather circular way, is when they say when demand balances supply, and then you say, well, what is demand and supply? They say, well, I don't really know, right? Huh? But this is how it works, okay? So this, you see, when you learn economics, they'll say, okay, equilibrium is when demand equals supply. So there's an important question you can say, well, if demand, usually what we think about it is the quantity demanded, right? And supply is the quantity supplied, all right? Now, in any transaction, those are always equal. How can you buy more than anybody else is selling, or inversely? So this idea of equilibrium is a little bit silly, thought about it in this way, right? In any transaction, you know, unless the goods are coming out of nowhere, you know, the amount sold is always equal to the amount bought. So in this sense, demand is always equal to supply and cannot be a condition for equilibrium. It's just sort of a condition for the continuity of the space, that there are no holes in it, all right? What then is meant by demand equals supply? Well, Samuelson's book, he wrote a book, a textbook, he goes to some length trying to explain the difference. He says what's meant by saying this is saying that there is no urge to buy more, that everybody, although the quantities are equal, somebody wants more than he's currently getting, and the other one wants to give up a little bit more than he's currently giving up. All right? So when they say demand equals supply, what they partly say is what the wants are, right? Huh? So the effort for the one to give it up has to be equal to the want of the other to get it. Huh? So what they're looking for is an equilibrium of forces then, in our eyes, all right? And that's equilibrium. Now, the problem that Newton had is that you can define, you know, you can say, you know, okay, equilibrium is when all forces are zero. And then you say, well, what's a force? Well, a force is a change in momentum, and that's precisely what you see when you're not in equilibrium. So the whole thing will be circular, okay? So he's got a problem here. So he's got to formulate the idea of rest as separate, okay? So the only way you can do that is to say that there's something called rectilinear motion, and that's motion going in a constant direction, an unchanging direction at a constant rate. So economically that will mean that both the quantities demanded of all the goods and the composition are the same, and hence the composition are the same, right? So we're going through a straight line in that space. And that's what we call rest. Still a little bit circular, but okay, this is how it's set up. Now you can say, well, I can never see that. And then the idea is, well, you have to imagine that that's the case. And that's what we call an internal reference frame. Inertial reference frame, all right? And that's where it stands. Now, there are some clever writers who then say, well, why couldn't we have chosen a different inertial reference frame? And in a sense, that's what was the case before Galileo. It wasn't, before Galileo, people didn't think that rectilinear motion going in a straight line was the ideal motion. What they thought was going in a circle was an ideal motion because that's how the planets moved, all right? So their feeling was the circle was the inertial thing, the thing you would do naturally, that God ordained. And that if you try to move in a straight line, well, you're deviating from the circle, all right? Now, it's actually possible to set up mechanics this way, except it gets hideously complicated. And what you got to see is that it's much easier to take rectilinear motion to do your definition of rest, all right? And then look at circular motion as a deviation from that. And where does it come from? Well, make it up. What shall we call it? Let's call it gravity. Huh? Okay? Where does it come from? Well, we don't really know. It's a space that is determined. Can you see it? I don't know, but it's there, right? Right? That's the way you fix this, okay? And then you get the easiest description. And then all your laws start to work. But if you're doing banking, you may be more interested in hyperbolic motion, and you say that is rest. And then you can take that to be the straight line. And in fact, there are manifolds where that is the straight line. The geodesics, just like there are manifolds on which a circle is a straight line. That's the Earth, actually, and the great circle is the straight line. It's the shortest distance between 2 points. So it's all possible. It's just that this is not done in Newtonian mechanics. And in parts of economic engineering, especially when these are commodities, we will also not do it. We think of the composition as being the thing that is invariant, as being the direction, okay? So this treatment of Newtonian mechanics, it focuses on just on commodity flows. Yeah, and when later we'll do the rotational analog and we'll start talking about credit flows, because then we talk about circulating money and that being the kind of rest state. You know, like in Dutch, giraal geld. Giraal is gyrating, it's turning. And that's the rest state. Okay, so there's a little bit more TMI here, but I think it's important to, it's a little bit of a subtle setup, and it all seems circular until you see that what we're really trying to do is make the easiest description possible of the world around us, and that's what Newton does, and we stick to that, okay? And we always try to box it around so that it sticks to this idea, okay? And then if you see an upward sloping demand curve, say, okay, we can't have that, let's fix it, you know, and find some reasons. And if you can't find them, just call them something. The word gravity came from Aristotle, who called it gravitas, something important that went down, right? Okay. All right, so much for the first law, right? So rectilinear motion, composition, and the quantity demanded are constant, okay? Then you're in rectilinear motion, and that you can take any of those as being an inertial reference frame, and if you're doing that, then you're at rest, and this is economic equilibrium. If you have one axis, it's called partial equilibrium. If you have two, it's also partial, but it's a little bit better. And if you have all possible commodities in the world, they call it general equilibrium. Of course, there are too many, so you're never going to fix this. And you'll see the way we fix it, we'll just take partial equilibrium for the n commodities we're interested in, and all the other ones we'll just put together in some variable that we call entropy. All right? But this is for later. So you just choose your thing, and it's always going to be some idea of partial equilibrium. All right?
Q's are also Q dots.
Yeah, Q's and Q dots. It's just a space spanned by Q's, but for every point Q, there is a possible Q dots there, okay?
Yeah, so all states.
Yes. Huh? That's right. Okay, then we talked about the second law, and Newton actually defines it. If you read what he writes, he says a change in the momentum, quantity of motion is proportional to the force. That's how he defines force. Huh? I don't think he calls it force a vis viva or something, or vis. Yeah, but in Latin he has another name for it. But this is how he defines it, okay? So from this follows, of course, this, right? The same thing. This is how we think of force. So he thinks of it as a small impulse, okay? This is what his definition of the motive force, and it's a 1. So notice before, he just says a force and it has a motivation. Now he tells you exactly how big it is, so you can quantify it. He quantifies it. He knows what momentum is because he borrowed that from Descartes, right, or Huygens. And then he says, well, let me see how much it changes in time, and that thing I'm going to call the force. All right? So a want causes over a small period of time a small increase of your willingness to buy or sell. right? Okay. So an economic force will change your price just by a little bit. That's the margin, at the margin, right? All right, so this is almost like a definition, right? So you start with momentum, you say, I know what it is to have no forces, so this price is the same, that's economic equilibrium. But now suppose I'm in this inertial reference frame, I've convinced myself of this, and now I see it moving anyway, changing anyway, direction or speed. Oh, must be a force. How big is the force? Well, I just check how much the momentum is changing. I take the speed, and the mass, and I just do this thing, all right? And then I know. That's what you do, right? First put yourself in an inertial reference frame, look at the thing, is it moving in a squiggly line, and is it decelerating, accelerating? Okay, that must be forces. What are the forces? They're this. Where do they come from? I don't know, I gotta go a little further. Maybe it's a spring, it's this, it's that, right? And that's what we do in economic engineering too. So we're in this inertial reference frame, we're at rest, we're at partial equilibrium or general equilibrium, whatever the hell we want. And then all of a sudden we see demand changing. Quantities demanded are changing, this is changing, There we go. So if I if I bring the dt to the other side here, and I plug in my definition of momentum or the demand line, I get the law of motion, as it is known, and this is called the law of demand. Hey. Oh, I had a nice call out. I lost my call outs here. There was I had here a nice call out from Marshall where he says what the law of demand is, and you will see that it's precisely saying this, okay? I'll put in the update on the slides later. So that extension of demand, so that the wants are always proportional to the change in the quantity demanded, which he calls the extension or the contraction of the demand. So I lost my call out here. That's not so important. And that brings us to the third law, and this is the one that I'll talk about after the break. And then we'll talk about the third law some more, and a little bit about the principle of relativity, and then talk about power and energy, and we're done. All right? Okay, let's take a short break. I don't want to take too long because we lost a little bit of time in the beginning. We left off at where I announced I was going to talk about the third law. Now, the third law is it's a very also. See, the problem is I don't want to say the most subtle of all three laws because they're all pretty subtle, but it is probably the one that's most misunderstood, although most of them are misunderstood, and also the one that I find hardest to fully comprehend, although I find them all hard to comprehend. Okay. But the way it's normally formulated is that action equals reaction. If you're a little bit more precise, you say that action is equal to the negative of a reaction. So we know we're always taught this, so you have two, or you have some kind of member like this, right? And you cut it in two here, and there'll be a force here, and then one is an action force, and the other is a reaction force. You can choose either one. All right? So the first thing you got to notice of this is that there are two members here, okay? So there are two pieces of matter that these forces are defined on, okay? Sometimes people are thinking that this is just another way of saying that in a free body diagram, all forces should add to zero. That's not quite true because it's not a spring force, is not really part of it, but this is the way Newton set it up. Okay, so he's just talking about these two forces that are always balancing within member. All right. So when when you have two masses working on top of each other, on each other. So this is the same thing you would like to see in economics, is that there's some way that your want is balanced by an effort on the other side. So you have to exercise your wants, and there's something that necessarily has to be there to work as the reaction. And this is what Marshall calls, he's very vague about it, but the word that comes the closest is an effort. So the idea is as follows. In order to exercise your wants, you want more apples, you gotta exert an effort. So you gotta like apply the labor force on something, or some other force, or sell something else, okay? Either sell your labor or do something else, okay? And that's what they call an effort. Now, the word effort is a very nice one, of course, because that's the same word that is used in bond graphs and all kinds of domain neutral things as the general force. That's the name for force or voltage, electrodynamics, or pressure, or whatever analog you have. So it's very, I mean, if you read Marshall 1,500 times, you still won't know whether this is really the case. But I've just decided that this is the way we want to do it because it just fits so well with the way we're dealing with efforts anyway. So the motive force is a want, and the reaction force to the motive force is the effort, okay? And it has an opposite sign. That is minus the effort. Although the terminology would imply the minus sign is built in. So that's the way I like to look at the third law, as the impact of the third law. And, you know, when you read people like Marshall, they are actually, when you start off reading his book, he has a whole set of chapters about how, you know, there are some, he writes, of course, in the 19th century, some people trying to use math in economics, and he doubts whether it's ever going to be useful. And he doesn't see it, and that's why his book is all just written in English, okay? Regular English. But he does make graphs, and from the graphs you can figure out what the math should be. That's how you kind of figure it out. But when he doesn't make a graphic, you don't really know, because it's never really defined using the language of mathematics, and he purposely doesn't do that. So in this type of effort, what you're doing is you kind of are searching and see how you can make this fit mathematics. Interestingly, Newton got a glowing review from some Frenchman, very highly placed, I forgot who also said, well, the contribution of Newton here is to take a bunch of ideas that were there by Galileo and others and translate them into mathematics, okay? So this translation step, where you take the intuition you have and then translate it to mathematics, is a big step, okay? And that's what you kind of got to do here, you know? So you got to say, well, okay, how am I going to interpret effort? Yeah, this. So Marshall has a whole chapter that's called as wants and efforts and their satisfaction. So we'll see that these are forces, and the satisfaction, this is going to be power. So the satisfaction of your want. But we'll see that in a little bit, all right? Now, what is the upshot of this law? What it really does, it allows you to define a couple of things it allows you to do. The first thing you see is that if you have a situation like that, and suppose I'm putting a force here, I'm pouring momentum in, and that will be pouring through here, is going there, and it's doing a reaction force. This is just indicating that the momentum is pouring out. So what this law does, it keeps track of the amount of momentum that went in here and goes out there, okay? And when they are coupled together, you're saying that momentum is in a sense conserved. It has to pour out of the member or pour into the member. And if the member is not moving, then obviously these actions have to be reaction. At this point, nothing is moving. There is no mass to move. Therefore, you need this. So one way to interpret this, there's several ways to interpret this, is that you get this law of momentum conservation. So momentum is something you can keep track of. Okay? Now, the same is true for a reservation price, or for prices in general, right? So you can keep track of them. So if I lower my price, for you, it will raise, your price will raise itself, okay? We'll see how this works. So we'll get a notion of conservation of price, but what does that really mean, conservation of price? That's silly. But then comes Joris' question, what is the difference between price and value? At this point, price will become the value, you see? Now, because value is a state variable, value, you can think of something that's poured into something, that is contained within the demander. All right? He assigns this value to it, right? So at this point, momentum becomes what we would call a state variable. Huh? Because it's not getting lost or coming out of nowhere, thanks to the third law, you know that this location of this demand, which is at this agent, he or she assigns a certain value to this that is equal, if you monetize it, equal to the price. Okay? That's the important point. Okay? So we can now think of demand as being some element, let's call it an I element for inertia, and inertia we know is the analog of demand. And what is its state? Well, the state is exactly the amount of value that that particular I element ascribes to it. And the quantification of that is precisely the price. Okay? That's important for the engineering of it. So at this point, we really have an I element. See, before, you don't really, you have an idea, you have, of course, this, but maybe what you're really saying, F dt is some variation of P. This is what the English call the impulse, right? So it's nothing that's really stored in something, nothing you can integrate, but the integration is independent of the path, right? So I can do the momentum is P, is the integral of dP, but what is the integral of some, this is nothing really, it's going to depend on what path I took. Only if this is a valid little differential do I know I can integrate it and do I get a state variable, all right? So the way I wrote this down is already sneaking in this law, but these are subtleties, okay? But it's important to realize that they exist, because in this way you see that we are finally at the point that we can actually write down, say, an I element or have momentum as something we can keep track of. And we can draw, instead of the state space, we can draw the phase plane where we have Q, but we dispense with the velocity, and instead we draw the momentum, you know? And we have a state variable. It's much better. Then necessarily velocity is not really a state variable. Momentum is. And we can do Hamiltonian mechanics, and we can define energy, and we can do all kinds of stuff. All right? So, the third law, that for every want, there has to be some effort. So you can't just go around and exercise your wants and do nothing. So like a real economy, right? You got to work if you want to eat, right? Okay. You get this notion of momentum. Price is really, you know, the value added, right? Huh? You can integrate it, and this integration only depends on the endpoint. Okay. This is what our government uses, right? So when they want to tax you, they look and they keep track of how you're adding value. So this want, you know, or this effort, they would call it, because it's a supplier who has to do it. Every effort is a little bit of this, and they will tax a little bit of it. So they will subtract some friction force from it, probably, right? And then they just work their way up like that, all right? So every incremental added value, they'll take there, whatever it is, 21%, some huge amount, right? So our government relies on the third law in order to enact this tax scheme, because there are people who try to dodge it, and the only way to dodge it is to somehow make prices out of nowhere or make prices disappear, right? They do that, right? They have all kinds of weird schemes, but you'll see that they're somehow doing this, and you can't really keep that all up for long. I mean, at a certain point, you fall through the cracks. It's just not economic. Okay? I want to spend a little bit more time on the third law. And let me first go to this figure and then talk about these more further details that I get from this conservation of mass. So the third law also tells you why the idea of economic equilibrium in terms of a demand and a supply line will work. You see, here's the funny thing. You know, economists, or these demand type of economists, they think of equilibrium as the point where these two lines cross, okay? And this is the equilibrium quantity right here, right? Some equilibrium quantity, I don't know. But how does that work? How do you translate that to mechanics? Is there one negative mass and a positive mass and a this and a that? I mean, how does that work? And you can have equilibrium of only one mass and inertial reference frame, and you put some springs on it. Why do you need to collide it with another mass? Why are all equilibrium situations collisions, you know? Here they obviously have two reservation prices. There's the supplier as is, and the demander. Now, it makes no sense. You can just have a demander who is in equilibrium with a spring, you know, storage. Why do you need that other guy, right? Okay, I need an inertial reference frame, but, you know, why some? So, but suppose you do, then how would this work? Well, here's how it will work. Well, all I did here was look at a change in momentum or price for the supplier, right? Now, this is, according to Newton, the negative of the change in the price for the demander. Now, you can just see that. Why? Because this line goes the wrong way. Really, that's because they run this axis the wrong way, okay? So you can just flip it around, and then you will see that it's indeed the negative, all right? Now, if that is the case, you can calculate how much the contraction of demand for the one is compared to the extension of the other, all right? So building in this, you'll see that this is how equilibrium sets in, and in fact, you'll see that this is a way you can measure. I think this is what, I think it says. You'll be able to see that if you look at the ratio of the contraction or the contractions of demand, then this is the same as the ratio of the price elasticities, all right? Now, this is the way you normally measure mass, measure inertia. Weight is a little different. You can have a balance, right? But that's when you have gravity. But suppose you have no gravity, all you can do is look at the acceleration of two bodies that are interacting with each other in a collision where you know action is equal to reaction, right? Well, this is how you do it. And in the same way, you can kind of see now what this is the price elasticity. So it is also a relative concept, okay? So this could be like 1 liter of water, like 1 kilogram, and then you can have an absolute number, but you can only look at relative masses. So what you could do here in economics is you look at a particular standard demand, right? And then you start looking at the ratio of how much the one and the other has to adjust their quantity demanded, and then you can find the price elasticities of everybody else. All right? This is the way it should be done. Now, why is this super clever? It's super clever because this is what happens. So you assume you know what an inertial reference frame is, you assume all this stuff, and then you say, well, okay, now let's see if it works. And then you see that you can get it to work if you fix this business. All right? So you can also see the definition of mass or price elasticity as precisely that thing that makes the whole construct work. Okay, that makes it so that an inertial reference frame is what it is, and that F is m times A, and this. Well, then how does that all work? Well, that works if the mass is chosen to be this. And then you can do mathematically clever guys can formulate that unless there are some special conditions, like with light or something like that, then this will you can always find this mass. There are some cases where you can't do it, right? Light is one famous example, a couple of other ones. Okay?
I don't quite see this picture and the explanation given with it, because I can see the point where they meet in an economic sense, but once we start applying the acceleration, then in this graph, the momentum would change. Do I have twice the momentum in the equilibrium point? Do I still have the same price even though I'm not in equilibrium, or do I get two different prices but constant total momentum? The analog here is lost on me.
Yeah, I think you're trying to read more in this than there is. You're trying to read in this a way in which you are forced to go to equilibrium. That's not what this is saying, okay? You will only get that if you add damping, for instance, some restoring force, all right? Huh? Okay, so what you need to see here is that if there's an interaction, then action will be equal to reaction. So if you want to keep here, then these things are going to be opposite effects, right? And the potential extension, these are all potential effects that may or may not happen, right? It's just giving you the relationship to what could happen if you have this collision, all right? So what you do is you take the third law, you think it through how that would work in this graphic that they have, and you see how these restoring forces all balance each other out, okay? So maybe I can just go on a little bit. I mean, it is a good question, and I find this also always hard to understand. But what's the main point here? The main point is that these two bodies are doing what they are. They're bouncing against each other, doing all this crazy stuff. And what is constant here, okay? Well, what's constant here is the motion of the center of mass, right? So you got this one body doing this, and the other doing that, and then here they collide, and then blah, 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 right? Huh? So these prices are changing all the time. This thing is like bouncing around, okay? Huh? It's not true that if you just take two bodies and you slam them together and you put a little bit of sticky thing here, then they'll move together as if they were one mass. It's not necessarily true, right? Huh? You could rig it up that way, but you got to put a lot of damping in here to get rid of that kinetic energy, right? Huh? Okay. But if you have elastic collisions, right, and I'm use elastic in our sense, then these things will move around, they're all weird stuff. But what will be constant is the center of mass motion. This thing will, from the outside, look, from somebody far enough away, now it will look as one thing moving along, right? So suppose you have a box with millions of these things, right? All, you know, I put 2 in this figure. I can put millions of them, right? All doing what they are, right? I don't know, okay. Then what's happening internal to this box is all this junk, all right? But the net effect, because of action and reaction, is that this thing has, the center of mass of this thing has some kind of resultant velocity, okay? And the action reaction is just takes care that all the internal forces cancel out.
So I have to read in this graph that equilibrium is the center of mass, the velocity associated with it, and the price is what exactly? The momentum of the
center of mass momentum, right? So the way you should read the law of conservation of momentum is that the momentum of the center of mass of the system that you're looking at is unchanged. Okay? That's the right statement of the law of conservation of momentum. So if you have a billiard table, and this whole billiard table is not moving, then you are bouncing around these billiard tables. That means that the whole thing is not getting a net velocity. You understand? That is the way you should look at this law, okay? So it means that the center of mass is at rest. That's what it means, okay?
yeah.
And why? Because internally you get all this crap going on, right? Of course, if this one is subject to a bigger force, there's no reason why I couldn't do that. But internally, you'll see, economists read this thing like that. So internally, if you're making this thing, then this guy has to react like that, that one to react, and then you can read off how their internal accelerations go. But you have to look inside of this thing, right?
Yeah, but that step is just not connected. I explained the equilibrium point where the lines meet, but what is the
yeah, but you keep not seeing that economic equilibrium can mean, in our case, that the body is at rest, that going at constant speed. You see?
Yeah,
You think it has to stand still here or something, right?
it can move at rest, just as we just defined it using Newton. But what is the rest of the line doing at this point?
Okay, this is,
In the graph.
this point here, this thing may be doing like this, and this one may be going like this, right? Who knows? They are connected through a spring, right? Okay? No problem, right? So there's no reason why this should, why it should not be oscillating. It could. You're assuming that the spring is always like the same length. That need not be the case. You understand? You have to see that our idea of equilibrium. Okay, here's what you got to see. This is that this thing is going at a constant speed. That is the microeconomic view. You just look at demand of this guy, this I element, okay? This guy going at a constant speed, that is the demand of this I element. This one is at rest. But what is the aggregate, what you call the aggregate demand? That is that the whole market, all the players together, the whole economy is at rest, okay? That is that the center of mass is at rest. That's an I element, and that is at rest, okay? That doesn't mean that the individual things are at rest, okay? So if you have a rigid body, a block, it's made out of atoms and they're all vibrating. But you don't care because you model that as one mass. All right? That's the same here. Like economists, they have two types of demand. They have this micro demand, that is this one person, agent, and then they have something they call aggregate demand. That is a whole economy or a whole market, and they have all kinds of conditions, okay? What I'm trying to tell you here is what you got to see is that the conservation of momentum gives you the idea of a center of mass motion that is in equilibrium, the center of the system as a whole, okay? And that gives meaning to the notion of aggregate demand, all right? Huh? So there's a connection between micro and macro, the same way we make a connection between the individual points and the whole system. All right?
Yeah, okay, I get that, but once we now increase, put force on supply, increase the price, right? Then looking at the graph, this would also increase the price of demand, because there's just one price. And then reading from right to left, demand graph, this would increase also the quantity demanded, but the quantity demanded is written off the other way. So somewhere there's something not conserved, right?
Yeah, I don't see that. And I just think that the fact that you have action equals reaction is that this force, the red force, equal minus the blue force, right? Means that the sum is 0, right? Which means that the whole center of mass, you know, is movement is 0, and therefore P is constant of the center of mass. That's what I see, all right? Although individually, you know, during a collision, they may exchange momentum, all right?
Yeah.
So I see a big box, right? Say a gas, right? All these guys are bouncing against each other and exchanging momentum. You know, now action is reaction during a collision, just like with billiard balls. You know, and they're changing these accelerations depending on the size of the mass. If the masses are all the same, like they are in a pure gas, you know, because the molecules are said, that's fine, it's all the same. It doesn't matter, right? That's what I see. But the thing acts as a rigid body with some kind of, and that's the meaning of this point. This point, the meaning is not that the individual guys are not like bouncing around it. No.
Yeah, so I said I understand the meaning of the point, but what if one of the billiard balls or the gas molecules is not at that point? Say you put a force on it, so it's above that point.
Yeah, but what's the problem? Suppose this box of gas is moving at 10 meters per second, huh? And here's a molecule that's moving to the left. Is it going at this point? No.
Yeah, but what is being drawn in the graph? What is the meaning? One molecule is going...
Now, you can't see that from this graph. This gives you just an interaction between two molecules, okay? And I'm trying to explain to you that when you're a collision, you only have conservation of momentum, action equal reaction at the moment of collision, okay? Huh?
I think I want to see too much in this graph.
I think so.
Okay.
But let's not bog down the whole lecture on this. I mean, it may be that I'm not explaining it well. I'll think about it, and maybe next week I can do a little better job, all right? Huh? But what you should have in your head is just either say a gas, right? And there are all these things moving around, or you can have a rigid body is going like that, right? Huh? And that's the aggregate demand. So it could be some market, okay? Now, this market, suppose here's this gas and you can just go through here, and you want to interact with this thing. You'll hit a molecule here, and then it will have a certain average momentum, then you'll hit this one, you'll hit this one. So it's almost like price is constant because there's so many, the average momentum is just going to be what we will call the pressure. It's always going to be the same. So the price is pretty constant, and this is what we will call a competitive market because they can interact all the time, all right? Huh? This thing, let me finish my lecture, Joris, for the moment. All right? Huh? Huh?
Do continue.
So, and this thing here is a little different. I mean, here you got to move the whole market at once, okay? This is like going to the ECB or something and buying up all their gold or whatever it is they have, you know, now, because they can, as soon as you buy here, this gets played on through that one and this one, you got to move all of them, all right? So this one has a huge, very small price elasticity, huge inertia, right? So you can see how with the third law, you can go from, you know, pure Newtonian. You see, the problem is Newtonian mechanics is all about a point mass and what is its velocity and what are the forces. But what Newton still had to do is he look at gravity of the whole Earth and whole motions of bodies. So then he had to imagine all of them being connected either to rigid bodies or springy bodies like the gases and other things, you know. And then when you make certain modifications, you'll see that, you know, you can actually model this and get pretty close to the actual behavior of these bodies, okay? And you develop a notion like the center of mass. And what it does, it just makes his laws useful, you see? Because without it, you would only know how individual points move. And as soon as you do anything, you'll have to, I mean, for a small box containing 1 mole of something, you got 10 to the power 24 points. How can you model all of those? You know, like you can't. Yeah? So you need some rules for how to average this all out. And that's what the third law helps you to get, okay? All right? So let's leave it for the moment at that, and then we can discuss this a little bit later, hopefully, and clear it up. This is something I did before. Let me skip this for now and work and use my last 10 minutes to address this other thing. All right. So now that we have Newton's laws in place and we know how demand goes and everything, now what are we going to do with this demand? All right. Now, what Marshall talks about is when you have a want or an effort, you got to satisfy it. It's something that can also always be satisfied. Another way to say that, if you have a want, right, you want to fulfill it. Now look at the word fulfillment. There is this filling, which is the flow. Which flow? It's exactly the flow of the commodity. So if you take some kind of want, that's a force, and you fulfill it, you multiply it by the actual stuff that you're getting in that's reacting to your wants, okay? And if you do that on the open market, this will be the rate at which you're fulfilling your wants. All right? So you take your want and you fulfill them. Another way to say that is I take this want and I fulfill them with a small increase in the commodity that I buy. All right? That's the way I satisfy myself. I could even think of this as my purchasing power, right?
What you have there is a dq dot, right? So on the power, those are q dots.
No. This is just force times displacement.
But force times displacement is not power, right?
No, it's PDT. So I'm multiplying it by a small, Okay, so power is this, right? And the power exerted over a small time interval is this. Because I just think that this velocity over a piece of time is going to be an increase in the amount that I purchased. All right? So, you know, the reason I wrote it down this way is because this is the way Marshall reasons. Like, you know, they think of a want more as FDT rather than the rate, you know? So this is a little bit of satisfaction you get. And if you integrate it out, you get the total satisfaction. And the power itself will be the rate at which this satisfaction is going. What is that? Marieke? Ja, maar dat moet ik eventjes... Did I answer your question, Jose?
Yes, you did. It's just the fact that you called you put the head in the power is a little bit confusing.
Yeah.
So maybe that should be I don't know.
Power times dt. Huh?
Yeah.
That's right. Yeah, I see that now. I hadn't thought of that. Thank you. Yeah, that's confusing. You know, I looked up this notion of power, and it was defined by James Watt, and he also meant this, and then later the dt was dropped. It's a little bit, it's funny, I mean, how these things go. So there is in my mind this confusion, but thank you for straightening that out. But the intuition, you see, all this talk about wants, and we now know what they are, that's all fine, but you still have to do something with your wants. You got to fulfill them. You got to you got to start, you know, getting stuff that's going to do something for you, huh? And that is this business. So the act of multiplying by the velocity is the act of taking your want and then filling it up, you know, with the flow of that commodity, okay? And that is the thing that will give you satisfaction, all right? This is just a definition, okay? This is just following Marshall's idea of fulfillments of want and putting it next to Watt's idea of power. Now, what you can do is say that this is not just an arbitrary amount I bought, but I place this in some kind of stock so I can keep track of it. So I know I have Q that independent of the path, I can integrate it. We'll talk about this later, some inventory, all right? And then you'll have something that is called an asset. Huh? Now this is called an asset. Here, this is not really an asset. You just bought it and then whatever you did with it, I don't know. Huh? But here you just hold it as an asset, and then the ones that are associated with it, or the effort you had to expend, what we think of an asset is what are they, what do they represent? They represent all these benefits you get out of it. You know, that's the way an accountant would formulate it. So this thing would be what you would call the marginal benefit. So a marginal benefit is something that you control, which is about your assets, and it's a slight detail as a difference with the act of actually fulfilling this want. And then you can integrate this out, and as you know, there's a difference between the work, that is just the total satisfaction, but that's going to depend on this path that you took. Or if you actually are the holder of the items and you put it in storage, then you can calculate what we call the potential energy. Huh? Okay? And that is the total amount of benefits that accrue to you from holding these items in your inventory. Okay? So, I mean, this all looks like just a bunch of definitions, and you know why it does? Because it really is, you know? The thing is, once we know what a force is, people were thinking about what work was, but they didn't really know how to define it. But with Newton's idea of a force, you can define, okay, we mean this with work, and this is potential energy, and all these things. And what I'm doing here is saying, okay, now that we know that a force is a want, and we have all these other concepts of space lying around of, you know, the quantity demanded or just a regular flow of commodities. We can do the same stuff, and we work through these things, and we start mapping this in ideas that are bandied around in economics, okay? And this is the way you're able to formulate these analogs to potential energy, other types of energy, and actually define it, okay? So once you know what benefits are, you're actually, and this is where I want to end the lecture with the next slide, you're actually on a roll. Hey, can you go to the next slide? Yeah. So now look what you can do. I mean, this is just called the work energy theorem. So you take a little piece of potential energy or work. Well, I just know that this velocity is the change of q by time. So I just write it like this. Then I use Newton's third law, you know, and I know that the reaction force to that must be, so this force is acting on some mass, must be p dot, a change in that momentum, okay? There's a minus sign that I pick up, all right? But I know that p dot dt is dp, and I find out that the work is equal to the negative of the change of kinetic energy. This thing is called the work energy principle, all right? But what did we do here economically? We say, well, we have these marginal benefits here, and all of a sudden, well, we are left with something that is called the surplus. So at any quantity demanded V, we can multiply that by an increase in the price dP, okay? And this is the amount that it was worth to us, and this is the surplus amount that we get from as a benefit from these items. So now we have a way of connecting the surplus to the benefits that can accrue from the ownership of an item. And the same way we connect potential energy with kinetic energy. And in fact, we can write down F dq plus V dP is 0, right? Which is the law of conservation of energy. So the law of conservation of energy follows from Newton's law. And what we see here is that the sum of the surplus and the benefits has to be 0, has to be a constant, okay? Now this is all going quite fast. Now I was going to come back to this thing of marginal cost and talk about how this works out in a typical graph of consumer surplus. We ran the end of our lecture, so I'm forced to leave more detailed discussion of this to next week. That's not a huge disaster, because what I see happening is I introduce a law or something like, and then it takes, you know, and then we come back to it, and then the understanding is deepened. And now what we have done is we brought in the third law and this notion of power and energy, and we'll really deepen it out in the next lecture. But now you have the first connection to it. So I want to leave it at that, and then wish you all a lot of fun preparing for Thursday. So Thursday we'll do two things. First, we'll have the final run of Gilbert, right?
Yep.
I want to keep that just to the 25 minutes that you're allotted, and then a little question and answer session, and then a little rundown from me, you know, on you know, what could be last minute kind of ideas, okay? So we can get that whole thing wrapped up in 45 minutes, then we'll take a small break, and then we'll continue our discussion on how to do the thesis writing and midterm writing, and take various reports, Joris and Wouter and Max Broekman. Okay? So see you all then.
Yeah.
All right.
See you then.
Thank you.
Bye.